Welcome back to the deep dive. Today we are diving straight into, well, the engine room of modern intelligence systems.
That's a great way to put it.
We're talking about the mathematical core, the computational foundations that allow everything from autonomous vehicles to pharmaceutical research to make sense of a world that is just inherently uncertain.
That's right. Our source material for this dive really maps out the rigorous steps needed to build truly intelligent decision-making systems.
And we can forget the buzzwords here, right? This is the fundamental question.
It is, how do you choose the optimal action when you have absolutely no guarantee of the outcome? Our mission today is to distill how these systems quantify doubt, how they structure vast amounts of knowledge, and then, how they actually act rationally when faced with these inevitable unknowns.
I love that framing, quantified doubt, because as you said, if the world were purely deterministic.
If everything was predictable.
Exactly. If we knew exactly what would happen after every single action, AI would just be a massive, maybe complex, but ultimately just a lookup table. But reality is messy, it's unpredictable, and a lot of the time hidden from us.
Precisely. And this interaction between the system and the world is encapsulated in what our sources call the agent loop.
Okay, so let's define an agent.
An agent is really any entity making choices. It could be a self-driving car, a factory robot, or even a piece of software optimizing energy usage in a building.
A physical or non-physical entity.
Right. And at any point in time, let's call it Taylor, the agent receives an observation of the environment.
And that observation is almost never perfect.
Never. So based on that imperfect observation and its own internal belief state, the agent selects an action. And that action leads to a new, and this is key, often non-deterministic state, restarting the entire cycle.
So it's a continuous feedback loop. Observe, act, observe again.
Always. And when you really break down that loop, you realize that uncertainty isn't just one thing. It's a whole spectrum of problems.
Our sources actually define 4 major sources of uncertainty that, fundamentally challenge these intelligent agents.
They do. And they are really the pillars of this entire field. The first is what's called outcome uncertainty.
Okay.
This is probably the simplest to grasp. Even if your system knows the state of the world perfectly, the result of your action is uncertain.
So give me an example.
Imagine a supply chain bot trying to grasp a package. Maybe the package slips, or maybe the motor overshoots by a tiny amount. The action attempt is certain, but the resulting effect is not.
Right. Then you have the second one, model uncertainty. This one feels deeper.
It is. This is where the agent doesn't actually know the fundamental rules governing its environment. The transition function itself, the mapping from an action and the current state to the next state, is unknown.
And that's critical because that's what leads us to things like reinforcement learning, right?
Absolutely. Model uncertainty is the problem that pushes the field toward those kinds of techniques. The agent can't just pre-calculate the best path. It has to explore the environment, learn the rules, and discover rewards through, trial and error.
So its model of the world is a hypothesis that's constantly being updated.
Constantly. Okay, so the third source is state uncertainty.
This one seems pretty intuitive.
It is. The world has a true state, but the agent cannot observe it perfectly. Sensors are noisy, data transmission can be unreliable, and crucial information is often just hidden, occluded.
Like an autonomous drone doing surveillance.
Perfect example. The true location of a target might be known precisely, down to the millimeter, but the drone's GPS signal is subject to noise, or its camera resolution isn't perfect. The agent doesn't see the truth. It only sees a noisy, incomplete reflection of the truth.
So it has to maintain a belief, a distribution over all possible real states.
I can't just know the target is at X. It has to think the target is most likely at X, but could also be at Y or Z.
And that brings us to the last one, and it feels like the beast of complexity. Interaction, uncertainty.
It really is. This arises when the environment includes other intelligent agents whose actions aren't just random noise, but are driven by their own unpredictable objectives and decision processes.
So you're not just modeling physics anymore.
You're modeling other minds. If you're designing a traffic management system, you need to predict not just the physical flow of vehicles, but the decision-making of every driver and every pedestrian. Their behavior is the largest and most complex source of uncertainty your algorithm has to handle.
And this all just shows why this research isn't just theoretical. The applications are everywhere, and the stakes can be enormous.
For sure. Take the example of aircraft collision avoidance systems, or ACS.
That's a classic one.
It's a fantastic example of a direct trade-off under uncertainty. The primary goal is, obviously, safety.
Of course.
which means you want early alerts to give pilots the maximum possible time to react. But if you set that alert threshold too low, what happens?
You get flooded with false positives, unnecessary alerts.
Right, which waste fuel, cause needless stress for the pilots, and they introduce their own set of risks because of these unnecessary maneuvers. The algorithm has to precisely calculate the probability of a collision in the near future and decide exactly where to draw that line.
And that complexity just gets amplified with something like automated driving.
Oh, that's a whole cocktail of state and interaction uncertainty.
Mm-hmm.
The vehicle relies on all these imperfect data streams, LiDAR, radar, cameras.
And those sensors are susceptible to everything: heavy rain, fog, occlusion.
Like a delivery truck blocking the view of a crosswalk. The agent has to integrate all that imperfect, noisy data into a single coherent picture of the world. That's overcoming the state uncertainty.
And then it has to look at that picture.
And rapidly predict what every other road user is going to do next. That's the interaction uncertainty. Is that parked car about to pull out? Is that pedestrian looking at their phone? Or are they looking up to cross the street?
That predictive modeling is what separates basic automation from true autonomy.
It's the whole ballgame.
My favorite example, though, has to be the Mars science exploration one.
Oh, yeah. The communication delay.
It's just brutal. A 30-minute communication delay. You cannot teleoperate a rover from Earth. It's impossible.
So the rover has to be a robust, self-reliant decision maker. It has to autonomously navigate this incredibly complex terrain, avoiding hazards like steep slopes or soft sand.
And it has to do science.
Right. It needs to analyze geological formations, prioritize scientific targets, and choose which samples to collect, all while dealing with these hugely delayed observations.
And the source material notes that just giving the rovers this foundational autonomy can improve operational efficiency by a factor of 5.
5. That's the power of moving this computational heavy lifting off Earth and onto the machine itself.
And that's the ultimate so what's for our dives today, isn't it? It's not just about small incremental improvements. It's about unlocking capabilities that were previously, physically impossible.
Absolutely.
So let's begin our technical deep dive. How do we take something as abstract as doubt or belief and actually quantify it so a computer can manipulate it?
Well, we have to start with the philosophy of belief, really. Rational decision-making requires some kind of unified system for comparing the plausibility of different outcomes.
It feels like probability theory is almost inevitable if you just start with a few basic rules.
It is. The mathematical foundation stems from a minimal set of logical axioms. Think of them as the rules that must hold true if you are to be considered a rational decision maker.
Okay, what are they?
2 key ones are universal comparability. You must always be able to say A is more likely than B is more likely than A, or they're equally likely.
You can't just say, I don't know.
You got to have an opinion, basically. And the other is transitivity. If you believe A is more likely than B and B is more likely than C, you must believe A is more likely than C.
And the incredible result of just adhering to these simple rational axioms is that your degree of belief, it has to be representable by a real valued function, P.
And that function P has to follow the rules of probability. Every outcome must have a likelihood between 0 and 1, and the sum of all possibilities has to equal 1.
And that gives us the common language we need to quantify uncertainty.
Right. And once we've quantified it, we use distributions to represent that uncertainty.
And we split the world into 2 types of variables here, discrete and continuous.
Yep. Discrete is easy countable outcomes, like a coin flip or counting the number of cars passing a point. For that, we use a probability mass function, or PMF.
And the critical constraint there is simple. The mass assigned to each point has to sum exactly to 1.
Right. Continuous variables, though, like temperature or speed, are trickier, because the probability of the value being exactly 20.0000 with infinite zeros
Is 0.
it's 0. So here we use a probability density function, PX forms. We don't focus on points, we focus on intervals. The total area under this curve has to integrate to 1 over the entire range of possibilities.
And listeners might have also encountered the cumulative distribution function, the CDF.
Which is simply the interval of the PDF up to a certain value x. It just gives you the probability that the variable is less than or equal to that value.
Now, for computational convenience, we tend to prefer certain parameterized families of distributions.
Oh, definitely. The simplest is the uniform distribution, where every value within a given range has an equal density. If you're modeling a random time of arrival, that might be a good starting point.
But the real workhorse of classical statistics and the mathematical favorite for its tractability is the Gaussian or normal distribution?
Of course, it's defined entirely by just two parameters,
Hmm.
the mean, which is the center, and the variance, which describes its spread.
The Gaussian is beautiful because it's so mathematically convenient. As we'll get into later, if your entire system is Gaussian, you can solve many complex inference problems cleanly just using matrix algebra.
But as you pointed out with the airplane example earlier, it has a pretty serious physical limitation.
Right. A standard Gaussian distribution mathematically stretches infinitely in both positive and negative directions.
So if we model the altitude of an object that can only exist above the ground, the Gaussian still assigns some non-zero probability, however tiny.
To the object being miles underground, which in the real world is a dangerous modeling error.
To correct for this, we use the truncated Gaussian. This is essential for building robust systems. We just define explicit lower and upper bounds, more dollars, and we integrate the standard Gaussian density only within that bounded support.
So it ensures we don't assign any probability mass to physically impossible outcomes, makes the model instantly safer and more rational.
Exactly.
But what if our uncertainty isn't just one smooth bell curve? What if we're tracking a ship and our sensors tell us it's either docked at port A or it's sailing towards port B?
The probability distribution of its location would have two distinct peaks.
Right, and a single Gaussian would try to average those peaks, putting the mean right in the middle of the ocean where the ship definitely isn't. It's useless.
That's where you need mixture models, specifically Gaussian mixture models or GMMs.
Okay, what's a GMM?
A GMM lets us combine multiple unimodal distributions, say 3 or 4 distinct Gaussians, each with its own mean, its own variance, and crucially, its own relative weight. By summing these weighted components, we can accurately represent these complex multimodal probability density functions.
So it perfectly captures that scenario where our object is definitely in one of several possible distinct locations.
Precisely.
So we figured out how to represent the uncertainty of a single variable, but now we hit the wall. The curse of dimensionality.
Yeah.
How do we connect hundreds or thousands of these variables?
And that's the real challenge of modeling reality. We need what's called the joint distribution, which describes the probability of specific simultaneous assignments across all variables, p, x1, openor, nupl, x2, tox, xn doppels.
The problem, though, is that the size of the parameter space required just explodes exponentially with the number of variables.
Astronomical. Let's say we have just 20 binary variables, so 20 on-off switches for components in a control system.
Okay.
To fully define the joint distribution, you would need 221 independent parameters.
That's over 1 million parameters for just 20 variables.
And for 50 variables, you're looking at quadrillions. Storing, computing, and most importantly, learning those numbers from data becomes completely impossible.
That is the curse in action.
It is. If we want intelligent systems that can manage hundreds or thousands of interacting variables, the full joint distribution is computationally intractable. We have to find some structure.
And the ideal structure, the dream scenario, is full independence.
Right. If all 50 variables are completely independent, we only need 50 parameters, one for each. We just multiply the individual probabilities together to get the joint probability.
But full independence is a fantasy in any complex system.
It is. So we have to land on the necessary compromise, which is conditional independence.
So we acknowledge that dependencies exist, but we assume that certain variables become independent if we know the value of some intermediate conditioning variable.
And this relies on the fundamental relationship of conditional probability and mechanism for reversing that relationship, Bayes' rule.
Ugh, Bayes' rule. Bayes b will equals pi I goals, all divided by PV. It's the bedrock.
It is. It allows us to update our belief in a hypothesis, $6, based on some new evidence.
And when we impose these conditional independence assumptions, we use Bayesian networks, or BNs, as the representation.
A BN is a directed for cyclic graph, a DAG, where the nodes are variables and the edges define the local dependencies.
And the magic is that we only need to specify a local conditional distribution for each node, $6.
Right, based only on its immediate parents in the graph, which we call Bapidai.
And this lets us factorize that massively complex joint distribution.
We use the chain rule for BNs. The joint probability of all the variables is simply the product of the conditional probability of each node given its parents.
Yeah.
Pi1n, Pi1 superdar.
Let's use that satellite monitoring problem you mentioned earlier to really show the savings here. We had 5 binary variables: battery failure B, solar panel failure S, electrical failure E, trajectory deviation D, and communication loss C.
Right. If we wanted to define the full joint distribution, We'd need 25 tilers, 1101, so 31 parameters.
But we can make some structural assumptions. B and S are independent, non-electrical causes.
And E, the electrical failure, is caused by both B and S.
Then E causes both D, the trajectory deviation, and C, the communication loss.
So with that network structure, B and S are root nodes. They just need one parameter each, their marginal probabilities.
E has two parents, B and S, so it needs 22, which is 4 parameters to define PEBS.
And D and C each only have E as a parent, so they just need 2 parameters each.
So we went from 31 parameters down to $1 plus 1 plus 4 plus 2 plus 2 plus 2 equals $10 parameters.
10. That is an incredible computational efficiency, and we achieved it solely by defining the causal and dependency structure in the graph. The knowledge representation itself is the tool that defeats the curse of dimensionality.
But those structural assumptions, the lines you draw, or more importantly, the lines you don't draw between nodes, they imply specific conditional independence relationships, which we write as KERP YZ.
They do.
So if I'm looking at a complex network, how do I know if 2 distant variables are independent given the evidence I have?
That's where D-separation comes in. It's the mechanism for reading those independence assumptions directly from the graph structure.
Okay, how does it work?
You examine every undirected path between X and Y, and you check if it's blocked by the set of evidence variables, Z. If all the paths are blocked, then X and Y are conditionally independent given Z.
And there are 3 basic network structures we need to consider when we're checking for a blocked path.
The first 2 are pretty intuitive. If you have a chain structure, so $6 to Y to Z, and you condition on the intermediate node Y, so you observe Y, then the path is blocked.
Like,
Because once you know the value of Y, knowing X tells you nothing new about Z, and vice versa. It's the common information bottleneck.
okay. And the second is the fork structure, $6 left arrow Y to Z.
Same idea. If you condition on the common cause, Y, the path is blocked. If I know the cause, the effects become independent. Once I know the temperature of the oven, Y, whether the bread, X, is burnt, tells me nothing new about whether the casserole, Z, is burnt.
Okay, that makes sense. But now for the third one, which is the most, I don't know, intellectually satisfying.
The inverted fork, or V structure,
Yeah.
$6 to Y, left arrow Z.
Here, X and Z are independent unless you condition on the common effect, Y.
Exactly. This is the key insight of explaining away.
Let's go back to our satellite. We have battery failure, B, and solar panel failure, S, independently causing electrical failure, E.
Right, so normally, knowing the battery failed, B tells you absolutely nothing about the solar panel S. They're marginally independent.
But
But if we condition on the effect, we observe that the electrical failure, E, happened. Now, B and S become dependent.
because they're competing to explain the failure.
They're competing. If we then find out that the solar panel S did not fail, that observation makes it much more likely that the battery B was the cause. The other independent cause has been explained away.
That is fantastic. D-separation formalizes that exact kind of human diagnostic reasoning.
It does.
So by the end of this foundational section, we've successfully created this digital scaffold for belief using BNs that lets us manage complexity and encode causality.
And now we have the model. The next big question is, how do we actually use that model to answer questions about the world? That requires the computational engine, inference.
So inference is the process of updating our belief. We have observed evidence, and we want to determine the posterior probability distribution over the variables we care about.
Right, and we do that often by marginalizing out or summing over all the hidden variables we don't care about.
To do this exactly, we rely on 3 core factor operations.
Yes, and remember, a factor is essentially just a table or a function that maps assignments of variables to a probability value.
Okay, so the first one is factor product.
Right. If you have 2 reports, factor A covers variables X and Y, and factor B covers Y and Z, the factor product combines them into a new, larger factor covering X, Y, and Z.
We multiply the probabilities, but we have to align on the shared variables, in this case, Y.
Precisely. Second, we have factor conditioning. This is how we inject real-world evidence into the system.
So if you observe that Y must be true, you just throw out all the rows in the factor table where Y is false.
You're slicing the probability space to match the observed reality. And third, factor marginalization.
Summation step.
That's the one. If we have a factor over X, Y, and Z, and we only care about X and Y, we sum up the probability mass across all possible values of Z. we're effectively hiding Z from the final result,
Now, if we were naive, we'd just multiply all the factors in the Bayesian network together first.
which would give us the full joint distribution.
And then we'd condition on the evidence and marginalize out the hidden variables. But we've already established that full joint distribution is prohibitively large. We run straight back into the curse of dimensionality.
We do. So we have to be smarter. We use an optimization called sum product variable elimination.
Okay, so what's the trick here?
Instead of one massive multiplication step followed by one massive summation step, variable elimination interleaves them.
It mixes them up.
It does. We process the hidden variables one by one. For a hidden variable we want to eliminate, say, dollars, we find only the local factors that involve all dollars. We multiply just those together to create a temporary intermediate factor, and then we immediately marginalize dollars out of that intermediate factor.
So you create a new factor that no longer involves dollars.
Exactly. We throw that new, smaller factor back into the pool and repeat the process for the next hidden variable.
The genius here is that by eliminating variables as early as possible, we prevent the creation of those huge intermediate factors that would just blow up the memory and computation required.
It's all about the order of operations. The order in which you eliminate the variables is critical. It dictates the size of these intermediate factors.
And here we hit another major computational roadblock, because while variable elimination is efficient for many real-world sparsely connected networks, for general, arbitrarily complex Bayesian networks, the efficiency game just vanishes.
It does. And that's because inference in general Bayesian networks is NP hard.
Which is a profound and frankly shocking realization that was a major turning point in AI research.
It was huge. We know this because computer scientists demonstrated that you can map a known NP-complete problem, like 3SAT, the Boolean satisfiability problem, directly onto a BN structure.
So if you could solve general BN inference efficiently, you could solve 3SAT efficiently.
Which would prove P equals NP, something that is widely believed to be false.
The practical implication of NP-hardness isn't that we stop trying. It means we have to stop pursuing exact inference for all cases.
Exactly. That was the historical pivot point. We realized we have to settle for being close enough, fast enough. We have to move to approximate inference.
And approximation means sampling, Monte Carlo techniques.
Right. We estimate the posterior distribution by drawing random samples from the network.
The most straightforward method is called direct sampling.
Super simple. You put the nodes in an order where parents perceive their children, and you just sequentially draw random samples from the local conditional distributions until you have a full assignment of values for all the variables.
And then you do that thousands or millions of times.
Right. And if we want to find popular goal, we count how many total samples are consistent with our evidence. 8 all. Then we count how many of those also satisfy our query, $6. The ratio is our estimate.
But the limitation is crippling if the evidence et al. Is rare.
Oh, it's a disaster. If et al. Only happens in, say, 1 in a million samples, we will generate 999,999 irrelevant samples, discarding virtually all of our computational effort. This massive waste makes direct sampling completely impractical for systems monitoring rare but critical events.
This leads us to a smarter approach, likelihood-weighted sampling, or LWS.
The core idea here is to generate only samples that are consistent with the evidence. When we sample a variable that is part of our evidence set, we don't sample it randomly, we just assign the observed value.
Which ensures zero wasted samples.
Zero. But if we just fix the evidence, we bias the results toward that fixed outcome. So how does LWS correct for that induced bias?
With a weight.
Exactly. It uses a weight. When LWS fixes an evidence variable, it calculates the conditional probability of that fixed evidence occurring, given the values of its parents. This probability becomes a multiplicative weight for the entire sample.
So a sample where the evidence was highly unlikely will get a very small weight.
And a sample where the evidence was likely will get a high weight. We then compute the final probability estimates using these weighted samples.
Now, LWS is much more efficient than direct sampling, but even it struggles when the evidence is globally rare.
It does. Look at the chemical detection scenario described in our source material. Let's say the probability of a chemical being present is only 0.001, but the system observes a detection. LWS might spend a very long time generating samples where the chemical is not present, 2C1, but which have a very high weight because the false positive rate, PD1C, is relatively high. It takes an enormous number of trials to finally draw enough samples where 2C11 to accurately estimate the posterior PC1D.
So the algorithm converges very, very slowly in these sparse rare event scenarios.
Painfully slowly. And this brings us to what is really the gold standard for these high-dimensional sparse environments, Gibbs sampling.
This is a powerful, elegant Markov chain Monte Carlo or MCMC technique that solves the problems of both wasted samples and complex weights.
It does. Gibbs sampling is dynamic and iterative. Instead of drawing a brand new sample every time, it generates a chain of samples where each new state depends only on the immediate previous state.
So you start with some arbitrary assignment that's consistent with the evidence, and then you begin iterating.
And in each iteration, you pick one observed variable, say the state of the battery, B, in our satellite, and you resample its value based on the current values of all other variables in the network.
And crucially, thanks to the structure of BNs, you don't actually need the whole network to do that.
No, you only need to consider the variable's immediate neighbors, its parents, its children, and the co-parents of its children. This localized group is called the Markov blanket.
The state of the variable is conditionally independent of the rest of the network, given its Markov blanket.
Exactly. So we can efficiently update our belief in one variable, B, just by looking at this small, localized part of the network immediately surrounding it. And then we repeat this update across the entire set of unobserved variables thousands and thousands of times.
And the mathematical property of MCMC is that this chain eventually converges to a stationary distribution.
And those later samples are drawn directly from the true posterior distribution. We get high-quality, unweighted samples that rapidly converge on the true probabilities, even when the events are extremely rare.
Which is why, in that chemical detection problem, Gibbs sampling was shown to hit the true 0.5 probability estimate much, much faster than either direct or likelihood-weighted sampling.
It's a remarkable computational breakthrough.
But let's not forget that one glorious, clean exception we touched on earlier. If we use the right distributions, we can skip all the sampling pain.
Absolutely. If we constrain our modeling choice such that the joint distribution over all variables is a multivariate Gaussian, the entire problem simplifies dramatically.
Why is that?
Because in that context, the resulting marginal and conditional distributions are also Gaussian. And if they are Gaussian, we can derive the posterior distribution analytically using closed-form matrix operations.
No iteration, no approximation, no sampling.
Just clean, efficient, linear algebra matrix inversion, matrix multiplication,
Right.
to solve for the exact posterior mean and covariance matrix instantly. It's the highest possible efficiency you can get, provided your real-world problem fits that Gaussian assumption.
Which many physical processes, like tracking objects with noisy sensors, often do.
They do.
Okay, so that brings us from the abstract representation of doubt through the computational engine of belief updates to our final challenge. Where do the numbers come from in the first place?
Exactly. We have the structure, the knowledge graph, but the edges in that graph are weighted by numerical probabilities, means, and variances. Parameter learning is the process of finding those numerical parameters, which we'll call theta, that define these distributions based on the data we observe.
And the simplest, most intuitive approach for this is maximum likelihood parameter learning, or MLE.
Right. The goal is straightforward. Find the parameter values that make the observed data deal dollars as likely as possible.
For standard models like the Gaussian or the categorical, MLE often just involves maximizing the log likelihood function,
which usually reduces to finding simple empirical statistics. For example, if you're modeling a categorical outcome, the MLE estimate for any probability is just the observed frequency, the ratio of times the event occurred divided by the total number of trials.
So in a Bayesian network, this is applied locally. For every entry in a conditional probability table, the MLE is just the ratio of observed counts.
Simple as that. And this method is easy, it's fast, and it's often accurate, until you run into the Achilles heel of MLE.
The zero count problem.
The zero count problem.
Let's ground this in a real system. Imagine a highly optimized automated freight train. Its system for collision avoidance has been trained on this massive historical data set.
Okay.
In the last year, there have been 0 head-on collisions at speed. Under MLE, the probability of a head-on collision is estimated
Is 0.
And the consequence of that is catastrophic.
It is. The model now believes a head-on collision is not merely unlikely or unobserved, it is impossible.
And any rational decision-making agent relying on this model will fail to allocate resources, computational or physical, to mitigate a risk it deems impossible.
And in discrete BNs with sparse data, this leads to computational nightmares where probability estimates are undefined, or you get NaN, not a number.
So we need a mechanism to stabilize our belief. to ensure that even if an event hasn't been observed, we don't treat it as impossible. We need to bake in a prior sense of skepticism.
That is the core motivation for Bayesian parameter learning. Instead of finding a single point estimate for the parameter phi, we treat the parameter itself as a random variable, and we estimate the entire posterior distribution over that parameter, p theta d.
This is where we bring in our prior knowledge and use Bayes' rule to update it based on the observed data likelihood to get that posterior.
The practical difficulty in Bayesian learning is choosing a prior distribution that makes the math simple. So we use what are called conjugate priors.
And they're convenient because when you multiply the prior by the likelihood in Bayes' rule, the resulting posterior distribution belongs to the same family as the prior.
Makes the math beautiful. For binary outcomes, like coin flips or collision versus no collision, the standard conjugate prior is the beta distribution.
And the beta distribution has two parameters, alpha and beta del, which play a really special role.
They act as pseudocounts or virtual observations. If we start with a text beta, 1, 1, 1, that's a uniform prior, our belief is equally spread between 0 and 1.
It's like pretending we've seen one success and one failure before we even start.
Exactly. If we then observe more successes and more failures, the posterior is simply text beta, 1 plus n, 1 plus m. The 1 plus m are those pseudocounts.
So even if we see 0 successes, $1 dollars, our system calculates the posterior based on $1 success and $1 plus m failures. The probability is no longer 0, it's a small positive number.
It forces the system to admit, I haven't seen this happen, but I know it's not impossible.
And for categorical variables with more than 2 values, the beta distribution generalizes to the Dirichlet distribution.
It does, beautifully. You just use a vector of pseudocounts, alpha $1, one for each category. We simply add the observed counts to these pseudocounts to find the posterior parameters. This additive simplicity is why Bayesian learning is so robust for sparse data in BNs.
But what if our underlying data distribution is so complex that a fixed parametric form, like a Gaussian or a beta, just fundamentally misrepresents reality? We might need something more flexible.
That's when we move to non-parametric learning. Non-parametric models are fundamentally different because their complexity scales with the amount of data, not a fixed number of parameters. They're designed to fit any shape.
And the classic example here is kernel density estimation, or KDE.
Right. If the density function is pol, KDE represents it as a sum of small kernel functions, typically little zero-mean Gaussians, centered at every single data point we've ever observed.
It's like sprinkling fine sand on a target. Each grain of sand is a data point, and the kernel is the tiny local pile it creates.
And the overall density of sand on the target represents the true probability density. If you get more data, the density representation just grows and gets more complex.
The key tunable parameter in KDE is the bandwidth.
Right, the bandwidth controls the width or the smoothness of those little kernels. A very small bandwidth means narrow, sharply peaked kernels. The resulting density estimate is bumpy and might overfit the specific data points we saw.
And a large bandwidth.
A large bandwidth means wide, overlapping kernels, which smooths the data globally, but could potentially miss fine-grained details. So selecting the right bandwidth is this careful trade-off between smoothing out noise and accurately capturing the true structure of the density function.
Now, in any real-world data collection effort, whether it's from a factory floor or a hospital, we run into the pervasive reality of missing data.
Oh, every time. Not every field is populated. It's a huge practical necessity.
The standard assumption we often have to make is that the data is missing at random.
Right, meaning the fact that a data point is missing is independent of the value it actually should have had. If we can assume that, we have options beyond just throwing away incomplete data instances, which is often far too wasteful.
The simplest solutions are basic imputation strategies where we just fill in the blanks.
We could use the marginal mean or mode, replacing a missing temperature reading with the average temperature ever recorded. But this fails spectacularly if the variables are correlated.
Right. If we replace a missing flight speed with the average speed across all data, we completely ignore the fact that the missing data point occurred when the plane was at 30,000 feet.
Where speeds are much higher than the overall average, you destroy the correlation structure.
So we need imputation that respects the structure of the network.
Exactly. We can use posterior imputation. We use our existing probabilistic model to predict the missing value based on all the observed variables for that specific instance.
So if our model is jointly Gaussian, we use that analytical closed-form solution to calculate the mean and variance of the missing variable.
And if it's a discrete BN, we might use Gibbs sampling to draw a value for the missing entry from the posterior distribution. This is much better because the imputed value is conditional on the surrounding observed data.
But wait, we've hit a kind of chicken and egg problem here.
We have.
We need the parameters, the padded luck, to impute the missing data, but we need the completed data to calculate the best parameters. How do we break that cycle?
That's the precise problem solved by the expectation maximization, or EM, algorithm. It's an iterative solution for parameter learning when data is missing, or, more generally, when latent variables are present.
And latent variables are variables we assume exist, but we never directly observe, right? Like the component assignment in that Gaussian mixture model we talked about.
Correct. In a GMM, we see the data points, but we don't know which specific Gaussian component, which hidden cluster, actually generated that point. The EM algorithm iteratively refines both the parameters and the missing information simultaneously.
It starts with an initial guess for the parameters.
Then it executes the E step, which stands for expectation. Using that current parameter guess, the E step calculates the expected value of the missing data.
So for the GMM, this means calculating the probability that each data point belongs to component 1, component 2, and so on.
Exactly. You don't fill in a hard value. You create a set of weighted completions based on the probability distribution over that missing information.
And once the data set is completed using those weighted probabilities, we move to the M step, maximization.
In the M step, we treat the weighted completed data set as if it were fully observed data, and we calculate a new improved set of parameters using standard MLE or MLP techniques. We're maximizing the expected likelihood of the observed data.
So the E step refines the data based on the parameter.
And the M step refines the parameters based on the refined data. And you just repeat this oscillation until it converges.
And the EM algorithm is guaranteed to find a local maximum of the likelihood function.
It is. It elegantly resolves the ambiguity of missing or hidden information, allowing us to learn incredibly complex models like Gaussian mixture models, even though we never actually see the critical latent component assignment.
We've really traveled from the philosophical requirement for rational belief, built the structural scaffolding to manage massive scale, developed engines for calculating that belief, and finally devised these iterative techniques like EM to learn the content of those models even when the data is messy and incomplete. #tag outro.
It truly has been a comprehensive journey. We began by establishing those 4 central sources of uncertainty that define the decision-making challenge: outcome, model, state, and interaction.
We quantified that uncertainty, translating abstract doubt into the rigorous language of probability, and we leveraged the structural efficiency of Bayesian networks and conditional independence to defeat the curse of dimensionality.
We then explored the computational realities of inference, accepting that exact calculation is often intractable.
Which necessitated the development of powerful sampling methods like Gibbs sampling to rapidly converge on accurate, approximate posterior beliefs, especially for rare events.
And finally, we detailed the necessity of robust learning, moving beyond the dangerous simplicity of maximum likelihood to the stability of Bayesian pseudocounts, and implementing iterative algorithms like expectation maximization to train complex models using real-world, incomplete data.
And these algorithmic foundations are not just academic exercises. They are literally defining the capabilities of the modern world. We saw the profound impact in high-reliability systems like aircraft control and rover autonomy.
But they are equally transformative in sectors like environmental sustainability, optimizing smart power grids, and tracking ecological health.
And in medicine, these probabilistic models are crucial for everything from improving diagnostic accuracy by integrating complex patient data to optimizing the very difficult logistics of organ matching and patient scheduling.
That's right. The ability to reason under uncertainty is what allows these systems to augment human intelligence across pretty much every field.
The ability of these algorithms to process noise and ambiguity has also pushed the frontier of what's possible in urban planning, too.
Allowing cities to dynamically manage traffic flow, optimize public transit schedules, and critically improve emergency response times by better predicting resource needs.
But we can't conclude without reflecting on the critical requirement that comes after optimization. We've focused entirely on finding the optimal decision based on the available data. But what happens if the data is flawed or the system is attacked?
And that's the profound final thought for you, the listener. Once a system is built using these sophisticated learning and inference techniques, it demands exhaustive robustness analysis.
We have to ensure the algorithm performs reliably, even when faced with highly improbable scenarios.
What we call rare event simulation. The system needs to be tested under conditions it has never encountered in its training.
And perhaps even more critically today, adversarial analysis. We have to ensure that these algorithms, which are capable of amplifying human intent on a massive scale, can't be manipulated by malicious actors through subtle changes to inputs or compromised data streams.
The future challenge is less about finding the optimal computation and more about ensuring the safety and accountability of the result. If these models are going to underpin our infrastructure, we need algorithmic methods to validate their performance against highly unlikely scenarios and potential manipulation.
That validation is just as crucial as the underlying mathematics, a perfect call to action for further exploration. Thank you for joining us for this deep dive into the mathematical foundations of decision-making under uncertainty.